Okay, so according to our textbook, so this is the end of this section. And we are supposed to move on to the next chapter about the conformal mappings. But I think there's one very huge important topic that was missing in our textbook. So I think this is the right time to introduce that. So which is about the winding numbers and Roche's theorem. Actually, the Roche's theorem is being introduced in almost all complex analysis textbooks. So yeah, so I cannot miss it. Okay, so today we're going to talk about the winding numbers. And a function, suppose you have a function f of z is, we say it, meromorphic function. Meromorphic in domain D if f is analytic on D, but except for finitely many poles in D. Okay, so this is our definition of the meromorphic function. Well, so far we have been discussing the poles or singularities of some functions. So therefore, so this time, so I want to introduce a slightly larger class of functions that also, which also allows the notion of the singularities. So this is our definition of the meromorphic function. And as you can see from this definition, the number of singularities should be finite. So therefore, all five singularities are automatically isolated singularities. And we are not actually allowing the removable singularities or the essential singularities. Well, because first, essential singularity is very hard to deal with. So this is the one reason that we are ruling out that essential singularities. And removable singularities actually doesn't mean anything. So therefore, if I mention the meromorphic function, then you should already automatically consider the singularities should be all poles. Okay. Okay. Now we have I have a function. This is a meromorphic function. And on D, and C is a simply closed curve in D. And so this is a big assumption, and F is analytic on the curve C, and F must be also non-zero on C. So that means for each point for each point of C, so your function value f of z never be zero. Okay. Now, okay. So, and I want to introduce the notion of the winding numbers. So what is that? So I have a function which is f, and for this time, I'm gonna consider my function as a function from two-dimensional space to the another two-dimensional space. So, for convenience, this complex plane has a z coordinate, and this guy has a w coordinate, and the function f is a map from this guy to this place to this space to that space. And I have some curve, simply closed curve that looks like this. This is C, and which is also positively oriented. And since f is a function, and f is never 0, so therefore I want you to consider the image of this curve under the function f. And and there is a very important condition. That is, my function f is never 0 on C. So therefore, the image of this guy under f is going to be another curve. This time, another curve in the W plane, but this curve cannot pass through the origin, right? Okay. And so maybe like this. And this guy, not necessarily positively oriented. Maybe this guy can be positively or negatively oriented, depending on the function f. And it never passes through the origin. And the image of this function may not be simply closed, because in this case, this guy obviously has a self-intersection at this point. So anyway, so this is this is what you can expect from this picture. And I'm gonna call this guy to be gamma. Okay, now what I want to do is this. Just choose any point from your curve C, and I'm gonna call it Z0. And this guy has an image on somewhere on this point. So I would say this is f of Z0. Now, what I want to do is this. Okay, respecting the orientation of your original curve C, I will travel along the curve C in this direction, according to the orientation. And as I travel from here all the way to and make a full circle, then the image will also travel like this. So this is negatively oriented. So, as I move from here to there, then the image will also move from here to there, and eventually, I will end up at this point. Just one more time. And what I want to do is I want to consider the phi 0 to be just any value of the argument of W0. So, argument is, not well defined. So which is always defined up to some integer multiple up to pi times 2. But you just choose any number you like. And once you have chosen your argument of phi of 0, then your argument will also change as you travel along this curve, along this image curve. And eventually, when you end up at this starting point, then you're gonna get some another number as your argument. So W1 is the argument of W. Yes, this notation is somehow misleading, but so you know what I mean by this. So even though this W0 and W means the same point, but the argument may be different because argument should increase or decrease. And this guy and this guy, the difference of this number and that number should be always some integer multiple of 2 times pi. Okay. All right. So the change of argument along the curve gamma, which is phi 1 minus phi 0. And this number is defined to be the winding number of curve C of function f, which is denoted like this. And this is, as I explained, always 2 pi times integer. Oh. So winding number of gamma is 2 pi I, 1 over 2 pi times this change of the argument. So basically, intuitively, you should understand the winding number like this. So winding number is you are supposed to count how many times you have wound the origin, right? And if you wound your origin in positive sense, say for instance, say twice, then the winding number must be 2, right? But if your image curve is wound the origin 3 times, then it's going to be 3. But if you wound your origin in the negative sense, 1 time, the winding number should be -1, and so. And just one crucial observation is when your image curve is not winding the origin, then your winding number should be always 0, right? I mean, so suppose that this is your image curve. Well, no matter how complicated your image curve is, but if this guy never wounds the origin, then the winding number of this guy is 0, right? Okay. All right. Okay, so if gamma does not wind the origin, then this winding number should be 0. Okay, so this is the winding number. Not a big deal. And there is a very important relation between the winding numbers and the number of poles and the number of zeros of your function. So it goes like this. Suppose that C is a positively oriented simply closed curve. And we suppose that number 1, F is meromorphic in the domain interior to C, and number 2, F is analytic and non-zero on the curve C, and the last condition requires a little bit of explanation. Then, sorry. is always z minus p. And where, yeah, I will need to explain these two numbers, z and p. Z is the number of zeros of f inside C, well, counting multiplicities. And P is the number of pores okay. So what do I mean by this? Well, what do I mean by counting multiplicities? So suppose that this is my curve C, and I have a couple of zeros. Sorry. And I have a couple of pores on here and there. P2, P1, and P2. And well, even though this one looks like I have two zeros and two pores, but well, suppose that the order of this guy is 3 and order of this guy is 2. And this is a simple pole, and this is the pole of order, let's say 5. Then counting multiplicity I mean by, and this counting multiplicity I mean by this, then we consider this point as 3 zeros, and this point has 1 zero, and this point has 1 pole, and this point has 5 poles. This is what I mean by counting multiplicities. Okay. Okay, so so therefore the winding number of your function about curve C is very close. Well, it turns out to be nothing but the number of zeros minus number of poles. Okay. Okay. Let me prove this. First, we will need to choose a parameterization of curve C from A to B. Be a parameterization of C. Now we want to consider this. F of Z minus F prime and dz. Okay, so this is very weird choice. Oh, sorry, yeah, I messed up. Yeah, my bad. Yeah. Prime should be on top and F of Z should be in the bottom. So, does it remind you anything? Well, for me, this one reminds me of the derivative of log of F of Z, right? If you take and C is a closed curve, right? Yeah, I know this doesn't make any sense, but which is, well, ln of the modulus plus I times the argument, right? And since this is the closed curve, the beginning point, the starting point, the end point, the modulus of the starting point and the end point should be the same thing, right? So this term actually doesn't matter. So therefore, what really matters after this computation, we can naturally expect this number should be somehow related to the difference of the argument. Well, when you travel your curve around this curve C, right? Okay. So so I think this is a very clever choice of integrand function. Okay, so let me check this out. So, well, now we have chosen the parameterization. So f prime of zt by f of zt, and z prime t and dt. Okay. So, and this is the curve. So this is the image of this curve. And this guy, we assume that this guy never zero. For all t. So therefore, it is okay to write this guy as log of t times e to the I times phi times t. So we are writing this guy in the polar form of the polar form. So now f prime z of t times z prime of t, which is the numerator of this integrand. And this is, no dt. This is, well, actually the derivative of f of z of t, but f of z of t can be written as the rho times t and e to the I times phi times t. So this is product of two functions. So we may use the product rule in this computation. So rho prime times e to the I phi t and plus, I times rho t times e to the I phi t times phi derivative. Okay, so this is the on the top, and the bottom is f of z is just this guy. So this one is from A to B. This guy is on the top, and rho t times e I phi t bottom and dt. Okay, and I have this factor is here and there, so these two factors can be canceled out each other. So simplifying this, I have rho prime over rho t, and these two guys, they cancel, and plus I times phi prime t and dt. Okay, all right. Now, this is about, well, this first term, this is about the real integration. So this is a, well, freshman calculus, well, this is the integration in the sense of the freshman calculus. So you know how to deal with this. So the first term is actually the natural log of rho of t evaluated from A and B plus I times this guy. And you know what? So since this is a closed curve, well, this image curve, which is gamma, so this is, well, this curve. This image curve is also closed. Therefore, the rho of A must be the same as the rho of B. So we can safely say that this guy goes to 0 as we evaluate from these 2 points and take a subtraction. So what really matters is that this guy, well, and this is what? This clearly represents the change of the argument as you travel the curve gamma from the starting from beginning to the end, right? So this is the number that we are looking for. So this is I times and the argument of f of z. Great. So we are done. All right. And on the other hand, there is a very interesting interpretation of the same integral. So on the other hand, we compute the same integration by using the residue. Well, because the Cauchy's residue theorem, this entire integral, so we are actually integrating. So this is the curve C, and we have couple of zeros and couple of poles inside, and we are taking the integral along this curve, but this integral is the same as this integration and this integration and this integration, that integration. So this integral can be broken down this 4 integration, not 4, but in this video. Well, this couple of finitely many integrations, and if we take a summation of all these guys, then this is going to give us this number. Okay. So let me just focus on this point, this integral. In order to integrate this, Yeah. In order to integrate this, then we'll need to take a small circle about this 0. But we are not actually taking the integral of f, but we are taking integral of f prime by f of z. So, well, and by the way, so I forgot to mention just one more thing. Well, we are assuming that f of z has a finitely many number of zeros and poles inside of C. Therefore, this integrand function f prime over f also must have the same finitely many number of poles and zeros inside of this guy. Okay. Now, first, we'll need to consider 2 different cases. Suppose that f has a 0 of order m at z0. This guy, this point is clearly inside of C. Sorry. Yeah. Just one more thing. Yeah, I keep forgetting. So how many singularities can you expect from this function? Well, clearly this function may have some singularities when f of z equals to 0, right? And in other words, the zeros of f should be considered as the singularities of this integrand function. And on top of that, well, this guy also has some poles inside of C. Therefore, the pole of f may be a singularities of this function too, right? If f has a singularities at some point, then f prime may have the same singularity at that point, right? Therefore, the poles of f can also be considered as a candidate of singularities of this integral function. Okay. So suppose that f has a 0 of order m at this point, then in order to compute this integral, then we will need to consider the residue of this function at this point. And since we are assuming that f has a 0 of order m, therefore the Taylor series of f about this point can be written like this. And g of z0 is non-zero. So this is the Taylor series of f about this point. Then f prime of z is just m times z minus m minus 1 and g of z, and plus z minus z0 to the m and g prime of z. So f prime over f is what is this? This is m over z minus z0 and plus g prime of z over g. Okay. Okay, good. Now, if you take a really small circle, if you just choose your circle to be really close to this point, then if the radius of your circle is small enough, then you know this guy, the function g of z0 is non-zero, right? Therefore, if z is really close to this point, then your denominator never be zero in that domain because your function g is always continuous, right? So that implies that this function is also analytic in the region inside of this small circle. Therefore, the integral of this guy should be zero. So therefore, the integral of this whole thing is only affected by this one, right? But so in other words, as the simple pole at z0, whose residue is just nothing actually, and its residue turns out to be nothing but the order of the zero, right? Okay. Okay, and the next, now we suppose that F has the pole of order M at some point. Then we can apply the same trick. Then f of z has a Lorentz series that looks like this, minus over z minus z0 to the m, and g z0 is non-zero. This is the Lorentz series. Then f prime of z is this is what? So m times z minus z0. Oh no, sorry, this is minus m, right? Yeah, and minus m to the minus 1, and g of z, and plus z minus z0 to the negative m's times g prime of z. So f prime of z over f of z is going to be what? So we have this, and this is a minus m over, I think this is z minus z0, and plus the same thing, yeah, g prime of z over g. Okay. Okay, the same trick. So so therefore, choosing the radius of circle to be small enough, then this guy goes to 0, and this guy is analytic, and therefore this pole integration is affected by this. In other words, this function has a simple pole at this point, and whose residue is this time around not plus n, but this is minus n. The signs are different. So as a simple pole at z0 with residue minus n. Okay, all right. Okay, so as a consequence, So which is just is which is the same as the okay, so just to make a conclusion, a zero of order m has, well, now we are talking about now we are integrating this large circle, which includes all the zeros and poles inside. And this integral is affected by the residues of each of these points, right? And the zeros, the zero of order m has a positive contribution by its order, and the pole of order m has a negative contribution by the order of this pole, right? So therefore, this entire thing is times minus number of zeros counting with multiplicities minus number of poles counting with multiplicities. So combining these two, so and also this guy was this, and then also I times the argument of f of z is 2 pi I times z minus p. So this is the winding number. The winding number is always the same as z minus p. Okay, great. Okay. So let me consider this. So I have a circle of radius 1, like this. And I want to consider the image of this guy about this function, right? But this is a z-squared. And the modulus of this point is 1. Therefore, the image of this guy is the same as this one, but this time around, but this image curve is winding the origin, not once, but twice, right? In positive manner. So we can clearly expect the winding number of this function about curve C should be 2, but the same can be concluded by just counting the zeros of this function enclosed by this curve, right? So this is the curve of radius 1, and clearly inside I can see just 1 zeros here. So there is 1 zero in the region enclosed by this guy. And the multiplicity of this guy is 2. Therefore, we can also get the same conclusion. The winding number is 2. What about this? So this is the 1 over z. So that means, this original curve, as we traverse this original curve in this positive direction, but the image curve is actually winding the origin in the negative direction, right? So therefore, this winding number, we can easily expect the winding number to be -1, but you know that you can get the same conclusion because, inside of this region, there is one simple pole at the origin, and therefore, by the previous theorem, we can also get the same conclusion, and the winding number should be -1. Should we try something more complicated than this? Like, Now, the behavior of, well, the image curve is not easily visualized before, but can you get the winding number of this function about the curve C? What do you think? Yeah, okay. So z cubed plus 2 by z. So, well, so inside of this region bounded by unit circle, well, I can see 3 zeros from the getting from the numerator, but these 3 zeros, I clearly think that the modulus of these zeros lies on the outside of the region, right? Right. So well, so it should therefore the zero the zero has no contribution towards the winding number. So therefore, what really matters is this pole at the center, at the origin. And since the order of this pole is just 1, therefore the winding number should be just -1. All right. Yeah, the idea of the winding number is very interesting. Well, especially for people like me, for topologists. So the notion of the winding number, the concept of the winding number, considered so important in so many different fields of topology and geometry and topology. But well, as an undergrad student studying the complex analysis, okay, why should we care about the winding number? Well, the next theorem gives you the idea why we should care about the winding number. Winding number actually gives us the idea to find the number of zeros of any given analytic function inside some domain. Yeah. I'm going to give you the statement. So this is the Roche's theorem. And it goes like this. I have a simply closed curve. And suppose that number 1, you have two functions, f of z and g of z, and they are both analytic in the region bounded by this curve. On the domain inside C. And the condition number 2, the modulus of f of z should be always strictly bigger than the modulus of f g of z on each point on the curve C. And so there is no numbers. Then the conclusion is f of z and f of z plus g of z have the same number of zeros. Well, this time around, so there should be no poles because we are assuming that these two guys are analytic. So same number of zeros, counting multiplicities. So these two functions have the same number of zeros in the region enclosed by curves. I think. All right. So I will show you the proof. All right. So first, so on this curve, we are assuming that the modulus of f of z is greater than modulus of g of z. So f of z plus g of z, this modulus is always bigger than well, this is a simple application of the tree guidance. Well, this is a simple application of the triangle inequalities. So this guy is always bounded below by this. But well, on this curve, well, this number is bigger than this, so this is always strictly bigger than 0, right? So this implies f of z plus g of g never be 0. On this curve. Okay. And also, we are assuming that these two functions are analytic. Therefore, they have no poles inside C. So this implies the winding number of function f. So this is z of f, and this is the winding number of f plus g. And so these two winding numbers are the same as the number of zeros of f and number of zeros of f plus g, right? Because these two functions. Well, why? Because this guy is bigger than 0 implies that this function never equals to 0 on the curve. So therefore we have this equality. And since this guy never equals to 0, gives us this equality. Okay. Okay, so so here I am intentionally writing down this guy as a product of two functions. And the argument of the product of these two functions, the winding number of product of these two functions must be the same as the winding number of the first function plus the winding number of the second function. Because, this can easily be justified by considering the polar form of these two functions. Well, ARG, f of z times g of z. So say that f of z equals to rho 1 writing down like this. So e to the I phi 1 t and a because suppose that these two functions never equals to 0 on this curve C, then because of this condition, we can also easily write down these two functions as in these two, like in the polar forms of these two. And this winding number is actually not affected by the modulus, but winding number is only affected by this argument. So therefore, f times g is going to be rho 1 times rho 2, and e to the I phi 1 plus phi 2. Okay, yeah, I am omitting t. Okay, so therefore, since this Therefore, this is the winding number of the first one, and this is winding number of second, the function g. Therefore, winding number of f times g must be the same as winding number of row phi 1 and phi 2 plus pi 2. So this is argument of f of z plus the winding number of this function. So, and now we know that this is 2 pi I times, sorry, not 2 pi, 2 pi times z plus g is 2 pi times zf plus this guy. Okay. So all we need to solve, well, it remains to show that this guy equals to 0. So if I can prove that this guy equals to 0, then this claim is proved. Let me call this guy to be, say, large f. I want to consider the modulus of this function. So which is just the modulus of f of z. And if this point z is a point on this curve c, then on this point on this curve, we are assuming that this inequality of these two moduluses. So f is always greater than g. So this means this should be less than 1. Okay. Okay, so what does it mean? This implies this. This is the domain, and this is codomain of function f. And well, this is the curve C that we are talking about. And this inequality set tells us, well, the image of this curve C must be some another closed curve in this W plane. But according to this inequality, the f of z minus 1. So according to this inequality, the image of this guy should be inside of the circle of radius 1, centered at this point. Okay, so that means the image of this guy is something like that. And I am pretty sure that this curve is not winding the origin of the W plane. So this implies, the image of C under F does not enclose the origin. Wind is the better notation. Okay, so this guy is. So therefore, z of f plus g is z of g. Sorry, f. Okay, great. Okay, so this is interesting theorem, but what is there any practical application of the Roche's theorem? Yeah, we have. The number of zeros. Counting multiplicities of z to the fourth plus 3 times z third plus 6 equals to 0. Inside the curve, this curve. Okay, so imagine that you are supposed you want to find the location of the zeros of this degree 4 polynomial. Well, if you know how to solve the degree 4 polynomial, but you know, so usually we do not want to make use of the what was it? The Cardan's theorem. I don't know. Well, so usually we don't want to solve the degree 4 polynomial. So how do you find the locate? Well, if we can actually, so if we can somehow approximate the location of the zeros, then that would be really great. And so, and in this case, we are wondering if there are any zeros inside of this circle. Now we can use the Roche's theorem. How? We are breaking this function into two different pieces. F of z is 3 times z third, and g of z is z to the fourth plus 6. And well, and so this guy can be taken as summation of these two. Now, when z equals to 2, the modulus of function f of z is what? It is 8 is 24. And the modulus of the function g of z is this is bounded above by, and we know that this number cannot exceed this by using the triangle inequality, and this is so 16 and 6, which is 22. Oh, okay, good, great. So the function f of z, whose modulus is always bigger than the modulus of g of g, right? Great. Okay, so comparing these two, and well, inside of this circle, I know that this function f has 3 zeros, counting with multiplicities, right? So therefore, f of z plus g of z has the same number of zeros inside of this circle, right? Has 3 zeros. Okay, so well, we actually, so this is not, this doesn't give you the exact location of the zeros of the given function, but now we somehow know that there are 3 zeros inside of circle radius 2, and the one last zero will lie away outside of the region. Okay, and I guess you are getting something, and if you repeat this procedure on and on, then you can actually get somehow approximate. Not you can actually pinpoint, but you know you can somehow approximate the location of zeros in this way. And the Roche's theorem gives us another proof of the fundamental theorem of algebra. A0 plus A1Z, AN minus 1 Z minus ZN minus 1 plus AN ZN, and AN is non-zero, has N zeros, counting multiplicities. Okay, so, well, I will need to make use of, in order to use the Roche's theorem, so I will need to somehow invent some clever breakdown of this function into sum of two different functions. And I believe f of z is ANZN, and g of z is the remaining terms. So why I choose like this? Because, well, because we want the modulus of f of z should be greater than the modulus of g of z. And if the modulus of z is large enough, then eventually this guy will be greater than this one. So this is why I have chosen it. Okay. Now we consider a circle whose radius r. And if r is large enough, then the modulus of z, f of z, should be greater than the modulus of g of z. But how large? This is an interesting question. So we'll need to figure out. So modulus of f of z on this circle is just an times r to the n. And the modulus of g of z is actually bounded by right? Okay. Now we are assuming just one more condition. Since we are considering the case when the radius of r is large enough, so it is clear that the radius of r should be greater than 1. So it is safe to assume that r is greater than 1. In this case, if r is greater than 1, then r n minus 1 plus a1 r n minus 1 a n minus 1 times r n minus 1. Right? Because we are multiplying a number which is greater than 1, so therefore this one should be bigger than this. And this is the summation of ai times r n minus 1. Okay, and in order to make use of the Roche's theorem, so the modulus of this one should be bigger than the modulus of this. So this implies that an times rn is bigger than, strictly bigger than. So r must be bigger than the sum of the moduli of all these coefficients from I1 to n minus 1 divided by the modulus of an. Okay. Aha. Great. So what does it tell us? What does it tell us? It tells us that if my circle is large enough, if my circle is larger than this number, then that tells us that the zeros of all zeros of this n degree polynomial is completely lying inside of this large circle. Okay, and the number of zeros of your polynomial is exactly n, counted with multiplicity. So I guess this is a slightly better proof than before. Yeah. So previously, before our midterm, so I gave you another proof of the fundamental theorem of algebra, but that only told us that for any given degree of polynomial, you're always guaranteed to find at least 1 zeros of that polynomial. Yeah, which is still nice, but that doesn't give us any idea about the location of zeros of your polynomial. But this proof also gives us, so also proves, not only proves the fundamental theorem of algebra, but it also gives us the idea. So where you should find the zeros of your function. Okay. You are supposed to find the zeros inside of the circle of this ring. Okay. So inside, so there are n zeros. And well, this is true for all, all radius r bigger than this. Therefore, you are safe to say that. So. Exactly. And all right. Good. Okay. Now we are on the final chapter, chapter 17, about the conformal mappings. So from now on, so far we were talking about the complex values functions, but complex values function should be understood as a function from the 2-dimensional Euclidean space to another 2-dimensional Euclidean space, F. So we usually said F can be broken down as a real part, U plus I times the imaginary part, V. So and U, it was a function of x and y, and V was also usually considered as a function of x and y. So this is an x and y, and this is u and v. So you may consider a function, any complex function, as a function from the space of x and y coordinate to the another space of u and v coordinate. And we want to somehow visualize the function. But the visualizing any complex values function is very much complicated because we are living in the 3-dimensional space. And so, just to consider any complex values function, then naturally you are supposed to consider a dimension which is higher than 4. But this is usually not possible. So therefore, visualizing or taking the graph of any complex values function is usually considered impossible. But however, we are still struggling to understand, somehow visualize the complex values function. That is, if we can understand the image of any given guy from your domain to your codomain, and if you can understand how these guys transforms under the function f, then this gives us the idea, some graphical idea also of the behavior of function. So for instance, can you visualize this? So what is this? So well, considering this guy as a transformation from R2 to R2, so what does it do? So you can actually consider this is a composition of A times B and plus B. And well, if you add some complex number by another complex number B, then you may consider it as a parallel translation by number b, right? So z to z plus b is a parallel translation. What about multiplying z by another complex number a? So you can consider it as a stretch or shrink and rotation, right? Well, suppose that what is this? So, in terms of the rotation and the parallel translation, I can say this function is actually stretched by factor of square root of 2 and rotate in positive direction by 45 degrees, then parallelly translate to the positive xy direction by unit 2. Okay, not a big deal. What is this? Oh, I messed up. This is 1 over z. So also I can say like this. This function is actually the modulus is taking the reciprocal, right? So let me say this is a unit circle centered at the origin. And if this guy here, then this point will be mapped to the modulus is now taking the reciprocal. So for instance, if this point has modulus 2, then the image of this guy now has modulus 1 over 2. Then now what? But this is not the image. But after this, after you shrink this, then you flip it about the positive x-axis, right? Because this actually tells that this actually is r times e to the I theta to 1 over r times e to the minus I theta. So this guy is now mapped to this point. Okay. So, and actually this function has very interesting properties. This function, you can consider this function is defined everywhere but except for the origin. But if we consider the extended complex plane, which is topologically homeomorphic to the S2, then you can think it as a function, one-to-one function from S2 to S2, which we will discuss in the next. Okay, yeah, thank you. Oh, by the way, okay, check this on your calendar, and if you have any problem, please email me. Okay, all right, good.